again. So last day we talked about central tendency. We talked about the main way of talking about the word average. The most common, of course, would be the mean. That's where you add up all the values and you divide by the number of values. Whether it be 5 values or 5 million values, it really doesn't matter. You add them up and you divide. Median, remember, is the middlemost value in a ranked set of values. I have to have a highest to lowest. If I just gave you a random set of numbers in no particular order, you wouldn't go after the one in the middle. You have to rank them first from highest to lowest or lowest to highest. Then you go after the middle. And finally, the mode was the value that occurred the most often. So if we're talking about votes or things like that, obviously the candidate who got the most votes should be the win. You don't average the candidates together. If we were talking about our favorite color, the color that got the most votes, we don't average the colors together. Or my favorite example is we talk about your favorite type of music. So we don't average all the music choices together. That would sound probably really terrible. Okay, so today what we're going to talk about is what's called variance. And it turns out in statistics, this is probably considered the most important topic. Now, what variance is a measure of spread. Now, I'm going to give you a really simple example. Let's suppose, and I use a lot of graphic pictures without numbers just to give you a simple illustration. Excuse me. I have a group of people and I want to measure their heights, and maybe there's a lot of people. There's a lot of people and I measure their heights. And when I measure their heights, I get something that looks like this. I get a curve that looks like this, different heights. And right here is probably the mean. Okay, great. So if I picked somebody over here, you'd say, wow, compared to the rest of the group, they're really tall. Or over here, compared to the rest of the group, they're really short. But you know, somebody here is pretty close to the middle. It's kind of easy to see that the illustration. These scores are not really heavily spread out, but we can see the spread. Kind of the bulk of the scores are right here to here. Is it possible I have somebody who's extremely tall or extremely short? Yeah, they would be the outliers as we talked about. Now, suppose I had another group of individuals and maybe the same number of people, and maybe even they have the same average, but they look like this. And so in the first group, most people are really close together in terms of height. The tallest and the shortest, there's not really a big difference between them. But in this group here, wow, there is a huge disparity between high and low, right? They're really spread out. But in both cases, maybe that's the mean. We'd say this group here does not have a big spread, but this group here has a huge spread. Does that make sense? So it would be kind of like this. And we're going to do every form of calculating today. So it might be, so Lila comes to me and says, Mr. Brown, I got 80 on my test. And I'll say, great, 80 out of how many? Okay, well, if she says 80 out of 80, I say, wow. If she says 80 out of 1,000, I go, oh. So 80 out of, she goes, oh, 80 out of maybe 85. Wow, good. How did the rest of the class do? Oh, the mean in the class was only 60. Wow. How was the spread of the class? Oh, the spread was really small. Well, I'm probably the highest score then. Or the spread was huge. I'm kind of in the middle. There's a lot of information that is beyond just what was my score. It's what was my score? How did everyone else do? Were the other scores spread out or were they tightly clustered? Am I above average? Am I below average? There's a lot of information that goes beyond just what is my score. And so we're going to look at all of those aspects and be able to say something, no matter what your score was, is there a way of determining how you did relative to the rest of the people? And a simple example of that is something like an SAT. Okay. Most of you probably took an SAT when you were in high school and you got a score, but what does that score mean? You know, I got 600 on my math, or I got, 440 on my English. You hear things like that. What exactly does that mean? We're going to talk about that today. We're going to know exactly what those kind of things mean. So, oops, let me grab my eraser here. What we're going to do is we're going to first define variance. Okay, now there's two variants. Last day we talked about the mean of a population versus the mean of a sample. I want to make sure we understand they're not exactly the same thing. They're calculated the same way, but one case, if I take a small sample and I find the mean of that sample, I'm going to use that to predict the population. Second way is I actually find the mean of the whole population, and that's absolute. So for a population, we called it mu, and that was the sum of all the scores over the number in the population. If it was a sample, we call it X bar. And it's the sum of all the scores over the number in the sample. It's the exact same formula. Big N is the number in the entire population. Little n is the number in the sample, but it's the same formula. Add up all the values, divide by n. Piece of cake. Now we're going to define variance. Variance for the population and variance for the sample. Now, this formula is going to appear kind of complicated at first because it's going to take some work with our calculators. But don't worry about that. I'm going to show you shortcuts. In a population, what we do is, and the term we use, I'm going to give you the letter really big. It's a Greek letter. It's called sigma. It's not an O. It's, you flip it, and it almost looks more like an R to me. But this is the Greek letter sigma. This is a capital sigma. This is a small sigma. So the summation symbol is actually called sigma also. So Greeks have, capital letters and small letters. So the Greek letter sigma, that's the symbol that we use for variance. So and variance is sigma squared, by the way. I know that sounds strange. Why isn't it just sigma? Sigma is something else. Sigma squared is the symbol we use for variance, and variance is as follows. It's the sum of every score minus the mean squared divided by the number of scores. We're going to go through that. So what I do is I calculate the mean first. Then I take every score and I subtract the mean, and then I square that value. The reason we square it is that now that makes it positive. You see, if about half the scores are below average and half the scores are above average, and I just simply take score minus mean and add them all up, they'd add up to 0, because all the stuff that's below would be negative, all the stuff above would be positive. That wouldn't be very useful. So we take the difference between the score and the mean and we square it. We add it all up, and then we take the average of those squared distances. That's variance. For a sample, the formula is slightly different though. And it's hard for me to explain why it's a different formula. When I took statistics in graduate school, I finally learned why. It has to do with things called bias, but don't even worry about that. The formula, and we use a different symbol, we use S squared. Sigma squared is the population, S squared is the sample, and we do the same thing. It's the sum of every score minus the mean quantity squared. Remember, we use a different symbol for mean when it's a sample, but the big difference is instead of dividing by n, we divide by n minus 1. That's the only true difference in the formulas. Rarely will you use this formula, because rarely will you have every single value in a population. Same thing here. Rarely will you use the population version. Okay. Now, there are situations where we would know a population. If a population is very small, we might be able to know every value. But more than likely, I want to find out about, Californians. There's almost 40 million Californians. So I'm probably not going to deal with the population. I'm probably going to have to take a sample because the population is just too darn big. But if the question involved, let's say things like testing positive for COVID, or have you been vaccinated for COVID? We actually have the numbers. We know how many people in California have been vaccinated. We know how many people in California have gotten COVID, or at least we've tested that many. So there are situations. We have a census, so we know actually how many people are in California. We know how many people are in each household. We know how many cars are in each household from the census. So sometimes we have population information. Most of the time we need samples. So we're going to be doing a lot of this stuff today, and I'm going to walk you through. We're going to do it with small data sets. We're not going to deal with thousands of numbers. We're going to deal with just a few numbers so that we can do it with our cheap calculators really, really conveniently. So let's start. I'm going to give you a set of values. All right. I sampled a group of Mesa College students and asked them how many children they have. Okay, students tells how many children do the students themselves have, and I got the following numbers. Okay, This is a sample of Mesa College students. I got 0, 1, 1, 2, 3, 3, 3, 4, 4, and 6. Okay. I sampled 10 Mesa College students at random, and I found out this is how many children each of them have. I would like to do the calculation to find the mean and the variance of these values here. Okay, so to find the mean, first thing we do is I need to add up the numbers. Now remember, this right here just means add them up. I don't need any special symbols. So when I add them up, let's all do that. So everybody grab your cheap calculator, and you might be able to do this in your head, that's fine. Tell me when you get a number, just holler it out. What do those add up to?
27.
27, good. And by the way, like I said before, always do it twice just to ensure. You say, well, why would I have to? What's the big difference? Well, you know, if I get the number slightly wrong, well, if I get the number slightly wrong, then every calculation is going to be wrong and my conclusions will be wrong. And yikes, you know, all hell breaks loose. Dogs sleeping with cats, the whole 9 yards. Okay, so X bar is therefore 27 over 10, or exactly 2.7. Real simple rule of thumb. Okay, the mean is always a quotient because it's the sum of scores divided by the number of scores. If the mean is not a terminating decimal, this is a terminating decimal, it stops. I didn't have to round it off. If the mean is not a terminating decimal, then simply use the fraction in all of your calculations. And the reason is, if you round it off and you're using the rounded off value in your calculations, you can be a little bit off later on. But if I use the fraction on my calculator, I can't have anything wrong. Now, how do we calculate the variance? Well, the variance is as follows. I take every score and I subtract this number. Okay, so it's like this: 0 minus 2.7 squared plus 1 minus 2.7 squared plus. And we're all going to do this. We're going to take our time, we're not in a hurry. 2 minus 2.7 squared plus 3 minus 2.7 plus 3 minus 2.7. I'm squaring each one of these. And I have 3 3s, and then 4 times 2 minus 2.7 squared. And then, and finally, 6 minus 2.7 squared. All over, what am I going to divide by? Anybody? Can you tell me? I have every one of these numbers minus 2.7, and then I'm squaring it. And all of this is my numerator. All of this is going to be divided by what?
10 take away 1.
So exactly
9.
9. Beautiful. By 9, not by 10, but by 9. So this is going to take us a moment, but let's take our time. Now, the thing is, on your calculator, you're going to need to use your parentheses key. So you quite literally enter it exactly this way. You enter parentheses 0 minus 2.7 close parentheses and hit the square button. So it's, you know, my screen looks like this. Okay, I just entered 2 minus 2.7 squared and then plus, and then I do it again. 1 minus 2.7 squared. So let's try this on all together then.
Professor, where's the squared button on the calculator again? I'm sorry.
Oh, so start with your open parenthesis.
I have that.
And then let's just start. So 0 minus 2.7, and now close your parenthesis.
Okay, got it.
Now you should have an x squared key. That's the easiest one. Or there's an exponent key, there's an x squared key. So I go boom, 0 minus 2.7, and then on my calculator, I have a key that looks like that.
I found it. Thank you.
Now that's going to square it. There's also an exponent key, but it's easier just to hit that. Now, don't total it, add that now. So we're going to square that, and then I'm going to say plus, and now do it again with this guy. Same thing. You should be able to put in a lot of numbers. Okay, This might take us a minute because this is unfamiliar territory for many of us. Now, before you divide it by 9, I'd like to know what your numerator looks like. So before you hit divided by 9, everybody go ahead and total what they have. So give me a total of this if you can, and tell me what you got. Okay, so I don't want to continue with the problem until we know we have the same numerator. Does anybody have a value yet? In other words, what's going to be on top here? So we want to go slow. What happens sometimes we hit one miss button? Oh man, I got to start over. Well, a lot of your calculators, if you hit a miss button, there's a key, the delete key, where you can just undo the last thing you wrote and then you can fix it. You don't always have to start over.
Professor,
Yes.
I was adding up the numbers, but can I ask, why is there a 4 times 2 minus 2.7 squared?
Did I? Oh, I'm sorry. That should be 4 minus. Thank you. That should be 4 minus 2.7 squared. Yeah, not 4 times. Sorry.
Oh,
Going too fast. Yeah, this minus this minus this minus. I'm doing each one. Now, some of you are clever. Some of you are clever, and you notice that didn't I just do this calculation 3 times?
yeah, I was gonna ask that.
Should I do this calculation and then just multiply it by 3? Can I do this calculation? Can I do this calculation to say times 2 because I'm going to do it twice? Is that legal, do you think?
Yeah.
Yeah. And when I'm doing this one, can I do this one once and then just multiply it by 2? Yeah. I mean, when we did a problem last day where we were finding the mean, remember I said you gave 500 quizzes? We didn't go 5 plus 5 plus 5. We took that number, we multiplied it by how many times it occurred. That's being lazy. That's a good use of laziness. So anybody have a numerator yet? I'm curious, because we all want to get the same thing here.
Is it
'Cause this-
30.9?
A little high. We got a different number? I did it twice also, just to make sure. Again, this squared, this squared, this squared. When I'm all done. And the nice thing about most of your calculators is you can see exactly what you entered on the screen. So if there's a miss, sometimes we miss the parentheses, or sometimes we just hit the wrong button. And that unfortunately can happen in real life. It doesn't matter if you have a computer. If you enter the wrong number, it's going to still give you, the calculation that you asked for, not the one that you want. No one else has this? Because this is why we have a calculator. I need everybody to do this because you got to know that you can do it.
I got 28.1.
28.1. Did anybody else get 28.1? 28.1 is correct, by the way. 28.1. Now, this is long, but it's not difficult. I just have to keep track. I have to say, okay, parentheses, number minus number, close parentheses, square, plus. Now, if you see the same calculation repeated over and over again, like, this one, you can do it one time and say times 3. If I'm adding the same number up multiple times, I can just say times, save myself a little work, but I've got to get that number at some point. So this is my variance. Now I can go ahead and divide by 9. And what do I get? I get 3.12, and I'm going to put a bar over the top. You guys remember what that means? When you put a bar over the top? What does that mean?
It just indicates that it doesn't stop.
Yeah, it indicates that number goes on forever. So it's convenient, it's lazy. Okay, so that's my variance. Now, What does that number mean to me? Well, it doesn't really mean anything to us yet. We're going to use it to do further calculations. But for this set of numbers, we just calculate this is the variance. This is the, think of it this way, sort of like the average squared distance that every one of these things is from the mean. Okay. Now, when variance is large, that means there's a lot of spread. When variance is small, that means these aren't spread. And so one of the most important uses of variance in real life, we use all the time, is in products, in machinery, in things like this. So imagine, if you will, I want to give you kind of a big picture. You have a bottling plant, okay? So, you know, bottles, maybe you're filling them with soda, maybe you're filling them with beer, you're filling them with something, filling them with water, but you have a bottling plant. You know, thousands and thousands of bottles are going through and the machines are filling them up. Great. But you notice when you get to the store, all the bottles are filled to different heights. Would that be a good thing or a bad thing, do you think, when you're looking at your own bottles? What do you think? That'd be good or bad? Nobody? Nobody? If I'm bottling tens of thousands, millions of bottles and they're all filled to different heights, good or bad?
Bad.
Bad, yeah, that's kind of a no-brainer, yeah. What would I really like? All of them exactly the same. Is that possible? Probably not perfect, but I would really like them to be the same. That's called consistency. I really want consistency. So if everything's always off, then we say they're not very consistent. If everything was pretty much the same, then that means there's no variance. Because if every one of the bottles is filled to where it's supposed to be, then every one of these calculations pretty much would be a zero, because it's what it's supposed to be minus the mean, it should be zero. Because I should be getting exactly what I want. If I want my bottles filled to 12 ounces and all of them are filled to 12 ounces, then the mean is 12 ounces and all the values are 12 ounces and their differences are zero. And in a perfect world, variance would be zero. Okay. Is that true in general? No, there's a little bit of variance. So I make things, I bottle things, whatever. I would like as little variance as humanly possible. Now I'm going to give you another simple example. Okay. Think of a restaurant. Okay, any restaurant that you like to go to and you go regularly. And most people I know, when they go to restaurants, they pretty much order the same thing. I'm one of those people. You know, I have my favorites, I order the same thing. When you go to the restaurant and you order that same thing, do you want it to be different each time you go? You order the same thing. So what you get, do you want it to be different every time you go? Or do you want it to be the same? What do you think? You're ordering the same thing from the restaurant every time you go. And so when you get that thing, what are you hoping for? Because it's your favorite thing. Anybody? You can speak up.
Yeah, you'd want the same thing, especially as a barista working in Starbucks. If you get different amounts of caffeine,
You got 10 orders of the same drink. Professional pride, don't you want to produce 10 exactly the same things? Or do you want 10 completely different things? It's the same order 10 times. You kind of want it to be all the same. You know, this person got a little more, this person got a little less, that person got a little bit better, that person got a little bit worse. No, you want it to be the same. You want consistency. In real life, when you don't want it to be different. So if you're ordering the same meal every time, you're ordering because you like it. You would like it to be that same meal. Not every cook cooks it differently. So the idea is, in real life, the most important thing that we strive for is consistency, whether it be restaurant, whether it be your coffee, whether it be the products on the shelf. I want consistency, because if there's large degrees of variance, then it means my products are all over the map. And by the way, in terms of money, you lose a lot of money in that case. You lose a lot of money when there's a lot of variance. So variance is a numerical way of measuring the consistency of whatever it is you're making. Now, this represented children from people. Okay, so people don't all have the same number of kids. Of course that's the case. But what if this measured something that I do every single day? I would kind of like to see the same numbers every single day, for example. Okay, now let's say you're a basketball player. We'll use that as a simple example. And you score 20 points every single night. Every night you score 20 points. Well, your mean would be 20. and every night you score exactly 20 points, your variance would be 0. Now you could take another player, they score 5 points one night, they score 30 points the next night, they score 16 the next night, they score 50 the next night, they didn't score the next night. They're all over the map. And their average is also 20 points a game. But their variance would be very large because the numbers are all spread out. So you would say, gee, the person who scores 20 points a night, they are very consistent. The person who scores 20, but their numbers are all over the place, they're very inconsistent. Now, you kind of like consistency, and no matter what you're doing, you kind of like consistency because it makes it easier to plan and predict. So variance is a numerical measure of consistency, but this is a really long-winded calculation. This is long. There's no way around it. This is the textbook approach, but I have a shortcut. I have a huge shortcut that I show all the stats students. I'm going to show you the shortcut, but the only thing you really need to know is the end result. The process is less critical, but I'm going to explain the process to you, okay? Because I can get the same number with significantly less calculations. Dealing with those numbers and that number, I can get to here much faster. And I think you would all like that, because using all the parentheses and closing it and squaring it, that can be a bit messy at times. So I'm going to show you a really handy shortcut. This is what we always use, actually. Okay, since variance is the following, okay, let's just do the numerator of variance. Don't worry about the denominator yet. Just let's consider the numerator. Now, the numerator for the population and the numerator for the sample, remember, it's the same. It's the sum of all the square differences. The only difference is, am I dividing by the number in my sample, or am I dividing by, you know, the number in the population or the number in the sample minus 1? That's the only difference. So the numerator is going to be the sum of each score minus the mean squared, or it's going to be the sum of each score minus the mean squared. But this calculation is the same. It's a number minus a number, and I'm squaring it. Okay. Now let's remind ourselves from algebra. If I said a minus b quantity squared in algebra, we know that's a squared minus 2ab plus b squared. I'm squaring a binomial and I get this, right? If I wrote them side by side, we learned this in algebra. It's a handy little shortcut. When you square a difference, right, you're going a minus b times a minus b, right? A squared minus ab plus b squared. Yeah. I got that. That's what I want to do with all these scores. I want to go ahead and square them first. Now that's a little long, but it produces a beautiful shortcut and result. So if I squared all these scores, what does this look like? This looks like x1 minus x bar squared plus x2 minus x bar squared. Remember, x1 just means first score, second score, and so on. I'm going to go dot, 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 all the way to the last score. Now, in our case, there were 10 of these, right? We said 0 minus 2.7 squared. Then we said 1 minus 2.7 squared, all the way down to 6 minus 2.7 squared. And then we did it on our calculator, and that was fine. I give you 10 values. What if I give you 100 values? Ooh, that would take a lot longer to do. So I would value a shortcut. So when I square this is going to be x1 squared minus 2 times x1 x bar plus x bar squared. That's what the first one would be. Plus x2 squared minus 2x x bar plus x bar squared. That would be the second one. I'm going to go dot, 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 all the way down the line, xn squared, 2xn x bar squared. Boy, did I make it better or did I make it worse? Well, we're going to gather all the terms, okay? So I'm going to start by first gathering all the squared terms. So I'm going to have x1 squared plus x2 squared all the way down to xn squared. That's my first. Then let's take all of these middle terms And you notice every middle term has a 2 and every middle term has an X bar. If every middle term has a 2 and it has an X bar, then I want to factor out the 2 and the X bar, and then that would leave X1 plus X2 all the way down to Xn. Okay, I'm factoring out the negative 2X bar out of every term, and what's left is this, okay? And then the last one is X bar squared plus X bar squared plus X bar squared. Exactly how many times? Exactly N times. And when you add the same number up N times, isn't that just N times that number? What do we got here? This looks kind of familiar. What is X bar? Isn't X bar the sum of all the scores over N? Isn't that true? Then is it also true that the sum of all the scores would be N times X bar? If I just multiply by N. Does everybody see that statement right there? We know this is true. This is the definition of the mean. The mean is all the scores divided by N. So that means all the scores must be N times the mean. I'm just multiplying both sides by N. Well, why is that helpful? Because that means that this here, this is the sum of all the scores. So that means this quantity right here is N times X bar. I have 2 times X bar times N times X bar. So that would be negative 2N times X bar squared. But then I'm going to add. So if I have negative 2 of something plus 1 of something, that's just the same as minus that thing. In the end, and this is the result I need everyone to see. In the end, I'll write it right here. When I do this part here, that's the sum of the squared scores. Minus 2 of them plus 1 of them is just minus that. That's my numerator. Okay, let me, you know what? I see a great glare right there. Does everyone see a great glare? Let me move it a little bit. Sorry, I'll put it underneath. When I do that, I'm going to get this. This calculation is so much shorter than the other calculation. And this is where it comes from. It's algebra. It's math 46 over and over and over again. I don't need you to know how I got everything. I just show you so I don't have to say, hey, here's a magic formula. No, I just basically squared everything, added them all up, and this is the result. This result is so much faster than the other one. So here's what I want to do. I want to do the same problem again. Let's use this shortcut. Now, what the sum of the squared scores means, quite simply, this guy here means you're going to say 0 squared plus 1 squared plus 1 squared plus 2 squared plus 3 squared plus 3 squared plus 3 squared plus 4 squared plus 4 squared plus 6 squared. That's what this says. You're going to square the scores and then you're going to add them up. So let's do this, okay? So now I don't need parentheses, I just need to hit that X squared key. So 0 squared, obviously that's 0 and that's 1. So I got 1 squared plus 1 squared plus 2 squared plus 3 squared plus 3 squared plus 3 squared plus 4 squared plus 4 squared plus 6 squared. That should be a fairly fast calculation. That's not really complicated. So everyone do that and tell me what you get. When you add up all the squared scores, what number do you get? Holler it out when you get one.
I got 101.
Anybody else get 101? 101 is correct. I'm hoping to hear everyone said, yep, I got 101 also.
All right.
Okay, so that's 101. Do we agree? So therefore, for this problem right here, I'm going to claim that S squared is 101 minus N is 10 because there's 10 scores. Now, here's what I'd like you to do. Don't divide by 9 yet. Just do the numerator. Everybody do the, because this is, we know this. We've already got the 2.7. That's the mean squared. Okay. N was 10. And you just added this up and got 101. So what numerator do you all get if you do this?
28.1.
28.1.
Hey, wait a minute. I've heard that number before. Isn't that the number we got when we squared each difference and added them all up?
Yeah.
The long way. We got 28.1. We got 28.1 when we did the big long problem. This problem here is less than a third as much work. It's about a fourth as much work in terms of button pushing. In fact, you're far less likely to make errors because when I have to open a parenthesis and I have to close a parenthesis and then I have to do something, we sometimes make errors because we forget to open it or we forget to close it. Something wonky happens. But when I just have to add up these guys, that is such an easier calculation. It's not even close. And you notice we got the exact same number. We're supposed to. We just got it a lot easier. So forevermore, when we're doing variance, there's a formal definition of variance, but this is a shortcut that is way faster. Now, if you go to Canvas and you look at the notes, okay, if you look at the notes section on Canvas, I have some notes on variance where I go through this and I explain it in great detail and I show you guys. So I want to do a few more problems where we just calculated just to see how fast we can do it. But there's one thing you have to have. You have to have the mean first because the mean is part of the calculation. Okay, so let's do this. Let's suppose, and let's do this. Let's suppose we had a group of scores. Okay, in fact, I'm going to do the UCSD example. Okay, the UCSD example. We're going to have N is 500 and we have a 5-point quiz. And I'm going to make up different numbers because I don't remember what numbers we used before exactly. So I had scores of 0, 1, 2, 3, 4, 5. This is why we have a calculator. So we don't have to do any of this in our head. So let's say that 16 people got this score and 58 people got this score and 102 got this score and 146 got this score. And hold on, I need my calculator now. Hold on a second. And 121 got this score. And 57 got this score. Okay, I have 500 students took a 5-point quiz and these were the scores. I would like to find the mean. I would like to find the variance. And that's a lot of numbers. Now, am I going to add up literally 500 numbers on my calculator? We're going to add up 500 numbers. Are you going to write 2 plus 2 plus 2 plus 2 plus 2 102 times? Come on. Now, don't we have a fast way of doing that? I think we do. So here's what we're going to do. We're going to do our calculations. We'll call it our intermediate calculations. In order to find the mean, I need the sum of the scores. In order to find the variance, I need the sum of the squared scores. So it's usually convenient to do them both at the same time, or one right after the other, let's say. So I want what are the sum of the scores, and I want what are the sum of the squared scores. Now, how did we do this one? Well, you didn't say 1 plus 1 plus 1 plus 1 58 times. You said, I have the score of 0 16 times. And then I have the score of 1 58 times. And then I have the score of 2 102 times. And then I have the score of 3 146 times. And then I have the score of 4 121 times, and then I have the score of 557 times. So let's do that first. Everybody in the class, let's do that. So we all make sure we have the same thing. This is being lazy. That's a good thing. Lazy means you're looking for shortcuts. Lazy means you're not going to sit there and actually add 0 plus 0 plus 0. I have the same number 146 times. I'm just going to say 3 times 146. A little more convenient. All right, so tell me when you have a value.
1,469.
All right, does anybody else get that same value? I'm going to wait for a moment. He said 1,469. I'm hoping everybody's doing this because you know, this is not exactly rocket science. Did you get that?
Yes.
Okay. This is arithmetic. This is not algebra. This is just adding numbers with a calculator. But if you don't use a calculator very often, there's some rust. And I want to make sure we all get the same number. All right. I've got that number. I'm not done. I got that number. Now let's do the sum of the squared scores. And how do I do the squared scores? I'd say 0 squared plus 0 squared plus 0 squared 16 times, or how about 0 squared times 16? Now I got to do 1 squared plus 1 squared. How about 1 squared times 58? 2 squared, 2 squared, 2 squared. How about 2 squared times 102? I think you guys kind of see the pattern here. I need to add up 3 squared 146 times. So let's just multiply 3 squared by 146. 4 squared times 121, and then 5 squared times 57. Again, same thing. Let's use our calculators and let's see what we get. And I'm going to do it twice. I always do it twice. All right, I got the same answer twice. I always feel good when I do it twice and I get the same thing. Then I know I did it right. And I know that's the answer. So somebody tell me when you got a number here, what did you get?
$5,141.
And you know what? We're on the same wavelength. That's what I got too. By the way, is this complicated? Is this complicated in any way? No, it's tedious. Never confuse the two. Tedious because I got to do a whole bunch of, but there's nothing about it that's difficult. So you have to be patient. Never be in a hurry when you have a calculator, because the calculator is already speeding things up tremendously. The problem with being in a hurry with a calculator is I make a misentry. That's it. That's it. If I'm in a hurry when I'm doing the calculator, I got fat thumbs. You know, if you ever saw me text, and when I'm done texting my wife, my conclusion is usually, that's not what I said. I misspell every third word because my fat fingers are hitting buttons all over the place because I am always texting in a hurry. If I just slow down, I said jokingly, but that's what you're doing. You're texting your calculator. Now, we are almost done. We haven't done anything yet. Nope, we've done all the heavy lifting. I need these two numbers, and here's how we're going to do it. All right here. X bar is that number over that number. That's X bar. Okay. And what does this come out to be exactly? So 1,469 divided by 500. Anybody? And there's no rounding here. I need the exact value here.
2.938.
2.938. Okay. Now we can calculate our variance. Based on what I showed you, the variance is minus N 500 times the square of this value divided by what?
– 500 take away 1 or 499.
Beautiful, 499. Is there ever a time I would divide by 500?
With the population, like the whole population?
If I said this is the entire population at UCSD, this is every student at UCSD and they just took this quiz. And by the way, this is one of those questions students will say, how do I know if it's a population or a sample? That should really never be an issue. In other words, the problem you're looking at, it should be self-evident. It should be very obvious without ever actually using the words. So I might say, every student at UCSD just did the following thing. Here's our numbers. And if we're only talking about people at UCSD, then that clearly would be a population. If I said 500 students at UCSD did the following thing, well, you know there's a lot more than 500 students, so that would have to be a sample. Okay, if I said Californians did the following thing, or 1,500 Californians did the following thing. Do you see what I mean? It's usually fairly obvious. Now, this, let me erase this just a little bit here. This is the variance. So let's do that calculation. Now, this is going to be a decimal value, so we want to be careful in our reporting. And I always do it twice. Does anybody got a number?
Yeah, but how many decimals do we have to like choose?
That
Or
is
we
a
have-
great question. That is a great question. There's no absolute rule, but the values I used were all integer values, right? I only used the numbers 0, 1, 2, 3, or 4, or 5. But you couldn't get a score of 4.7. You could get a 4, you could get a 5. So we're using discrete values. We gave the mean exactly. A good rule of thumb on the standard, or excuse me, the good rule of thumb on the variance is to go at least 1 decimal place more than these values. In this case, I'd probably go 2 decimal places because there's enough information there. Okay, so what number do you get on your screen if you go 2 decimal places?
1.65.
About 1.65. Now, there is a symbol, by the way, and a lot of you are not familiar with it. We use this in higher level math classes and in physics and stuff. The number on my screen is an infinite decimal. Agreed? And if I try to write down an infinite decimal, well, that takes a really long time because it's infinite and I'd be writing, well, forever. But there's a sense of practicality. If you agree we only need a couple of places, how do I indicate that I'm rounding off as opposed to saying, this is exactly this? I use an equal sign because it's exactly this. The variance is exactly this. I use an equal sign, but now I rounded it off. The symbol, believe it or not, some of you may not be familiar with this, the symbol that indicates that you rounded it off is you put a little dot over the equal sign. That's it. That symbol means that this is what is called an approximation. And a lot of people misuse that term. We do approximations all the time. By the way, has anybody filled up their gas tank recently in the last few days?
Me.
Yes.
Okay, so when you went to the gas pump and it said 439.9 cents per gallon with the 0.9, it always amazed me. And then you're filling it up and you're looking at, and it's saying, you know, you got 11.2379 gallons of gas. It gives you a whole bunch of decimal places. Agreed? You got a whole bunch of decimal places on your gallons. You have a whole bunch of decimal places on your price. But then at the end, it says you have $47.39.
$47, that'd be fantastic. I drive a truck.
Yeah.
But you know what I'm talking about? When you're looking at the gas pump and you're paying your bill, it's giving you dollars and cents. But think logically for a moment. Your dollars was $4.39.9. There's 3 decimal places after the dollar. And then when you look at the volume of gas, it's usually 3 decimal places. When you multiply a 3 decimal place number by another 3 decimal place number, you get a 6 decimal place number. That means every time you fill up with gas, your price should be 6 decimal places long. But because money only goes to 2 decimal places, every time you ever fill up on gas, it's rounded to 2 decimal places so that you can pay dollars and cents. You may not even have realized that. That's an absolute. Every gas pump in the United States gives a 6 decimal place value, and then you see 2 decimal places. Again, the volume, how many gallons, was 3 decimal places, and the price was 3 decimal places, and those are multiplied together, but then rounded. So every time you get gas, when you go to the grocery store or any store and you're buying your whole thing, and then they add the tax is 7.775%, I believe. Am I right? Is that sales tax? I sometimes forget. 7.775%. So when you're paying your sales tax, I guarantee you, it's way past the pennies, but then it's rounded to the nearest penny. So again, every time you pay money, you're probably doing one of these. And that's okay. We have no problem with that. I don't really need to know the 9th decimal place. So this is my variance. Okay, now that number by itself doesn't mean a lot to us yet. We're going to use it in further calculation. My first goal today is, how do I actually calculate the variance? And you guys you realize you just did something really cool. I gave you 500 scores. I gave you 500 scores, and you computed the mean and the variance in about a minute or two with 500 scores. Think about that. That's kind of cool. I didn't have to sit there and enter every number. That I'd still be entering the numbers if that was the case. I use the fact that we have the same values over and over again, and so I can just say this times 16, this times. And that was quick. And then the same thing when I squared it. I didn't have to say 0 minus this number, quantity squared. I gave you a shortcut formula. That's the sum of the squared scores. That's the number of scores. That's the square of the mean. That's the number of scores minus 1. And that's a standard all the time formula that we're going to use all throughout statistics. You're going to actually get probably pretty fast at this, especially if you have a calculator that you're very comfortable with. Now, some of you actually had really fancy graphing calculators. I have nothing against fancy graphing calculators, but when you're just doing short, simple calculations, sometimes the fancy calculator can take longer. I like cheap calculators when I'm doing this kind of stuff, because all of the numbers that are all the symbols that I want to use, they're like a main key. You know, I don't have to search. I don't have to go through menus. I truly don't care what calculator a human being uses, as long as you are comfortable with that calculator, as long as you are confident that you're entering things. There's nothing complicated here, but it's tedious. I had to enter a bunch of stuff, and I did every one of these twice because I want to make sure I got the right number. Okay, now we're going to take a short break because we've actually been at this for over an hour. We're going to take a short break. Then when we come back, we're going to talk about, how do I actually use variance? I mean, where do I use this to answer questions? And that's the coolest part. And you're going to see things that have been going on that you weren't even aware of. Conclusions are made, and now you can say, I understand how people made those conclusions. Okay, so let's take a short break, some air. So if I want to talk about a measurement of variance in a real life scenario, the example again might be, how long are customers having to wait from the time they order till the time they get their meal? And that's really not a difficult thing for a server. They have a running clock. They can have a stopwatch. And maybe over the course of a week or two, I collect a lot of data. I have hundreds and hundreds of customers, and I'm collecting the data of how long they're waiting. And I'm looking at the numbers and saying, most of the numbers are pretty close together. Maybe all the numbers are between, 12 and 18 minutes, let's say. I would feel pretty good. I'd say, we're pretty consistent on getting the food out. But if I was looking and I say, these numbers are really spread out very far apart, everything from 2 minutes to 2 hours, and go, wow, we're really inconsistent. Variance is a numerical measurement that helps you determine consistency of whatever it is you're measuring. We sell tires. Okay, if you bought new tires, usually your tires come with some kind of a warranty, like they're going to last 50,000 miles or they're going to last 60,000 miles. So let's suppose that we sell tires, but people are coming back after 20,000 or 30,000 miles and saying, my tires are completely worn out. You say, wow, that's really soon. I was kind of hoping it'd be closer to what we said, 50,000 or 60,000. Somebody else might say, gee, I got 100,000 on mine. Well, That's unlikely, but same idea. If the spread of the life expectancy of your tires is huge, then we have really inconsistent tires. So I'd like to know, this consistency aspect. Now, because variance is the square of the distance from the mean, maybe the square root of variance might even be something that is more meaningful. And turns out that is the most important part. We're going to define something called the standard deviation. I think somebody used that term last day. The standard deviation. Okay. If it's a population, the standard deviation is, drum roll please, sigma. Which, by the way, is equal to the square root of sigma squared. Meaning I calculate the variance and then I take the square root and that gives me the standard deviation. So in the sample, it's S, which is the square root of S squared. So you can't, no, move that over. You can't find the standard deviation without finding the variance first. Now, what the standard deviation is, and now this is really huge. Okay, let's suppose, let's keep it really simple. We're talking about test scores, okay? We just did an example and we found the variance. Each score represents something, but the variance was the square. So the units for variance would be a squared score, and a squared score might not be that meaningful. Let's suppose we were talking about waiting times at the restaurant, okay? And 15 minutes, 20 minutes, 60 minutes. The variance would be the square of the time, because that's the units. I'm squaring the difference. The standard deviation, because it's the square root of the variance, the standard deviation will always have the same units as the thing you were measuring. So if we were talking about waiting times, and I talk about the mean would be the average waiting time, variance would be the square of time, so standard deviation would be back to time again. So the standard deviation is a more meaningful value in terms of units, because it has the same units of whatever it is I'm measuring. So if variance is sort of like the average squared distance every score is from the mean, the standard deviation is more like the average distance every score is from the mean. Okay, so if the standard deviation is large, that means on average, my scores are really spread out. If the standard deviation is small, then it means in general, all my scores are tightly clustered. If we were talking about products or waiting times at a restaurant, we would want the standard deviation to be very, very small. Again, we like the consistency. If I was giving a test to a large class, I don't expect everybody to score the same amount. I expect there's going to be scores that are really large and maybe scores that are small. So the scores are probably going to be somewhat spread. But if the standard deviation is small, that means my scores are tightly clustered. Remember the example I did? I have the peak that's really tight. That would be a small standard deviation. If my scores were like this, that would be a large standard deviation. So standard deviation is kind of like saying, again, the average that scores are away from the mean. So now I want to go back. I'm going to do a new example. All right, we're considering, excuse me, we're considering all of the billionaires in California. Now, there's probably not a lot of billionaires in California. Yeah, Robert, do you have a question?
Yeah, I had a quick question, sir. My apologies. I know you said it, but I wasn't able to get it down real quick. What was the definition of standard deviation again? Just a quick math.
It's the square root of variance.
Square root variance. Okay, square root.
So if variance, the symbol for variance is sigma squared for a population, it's S squared for a sample. So sigma and S would be the standard deviations, which if you think about it now, that kind of makes sense because variance is the average squared distance and standard deviation is kind of like the average distance that every score is from the mean. Then the units make a little more sense. Now, let's suppose we're considering billionaires in California. Would there be millions and millions of people in my population? Billionaires in California. Or do you think it's probably really small? Anybody?
Not that much, but
yeah,
there would be.
Probably not that many billionaires in California. I doubt there's a lot of billionaires in California. I'd say probably less than 10. So we're going to consider the population of billionaires in California. And we want to consider, again, the number of dependents. Now, number of dependents isn't necessarily the same as number of children, is it? Number of dependents. Does anybody here remember when doing your taxes recently, either this year or last year? Well, first of all, is anybody here a head of household? You're one of the heads of your household. Anybody? Just pull her out. In other words, you don't live with your parents. Nobody? You all live with your parents? Come on, some of you are on your own. Now, when you're doing your taxes, first thing they ask you is, can somebody else claim you as a dependent? Okay, if you say no, that means you could be the head of your household. So in my household, I have kids, I have a spouse, and my parents live here. So I guess technically I live with my parents, right? We took my parents in a number of years ago. My dependents are my children, my wife, and my parents. So you understand what I mean by dependence is more than just your kids. If you have other people living, you might have friends living with you that you are supporting. So the dependents are kind of like how many you're supporting. So we got all the billionaires in California and we asked them how many dependents you have so we could do some statistical analysis. Okay, so when we asked them how many dependents they have, here's what we got. We got one of them had one had 4, one had 5, one had 7, one had 9, and one had 12. That person was very busy. Okay. In fact, actually, let me make that one 13. They take care of a lot. They have a large entourage, as we'd say. At 13. So here's what I'd like. I want to find mu and sigma. Now, I'm saying we're pretending that there are 6 billionaires in California. That's it. By the way, I don't know how many billionaires in California there are, but I doubt there's more than 6. Okay. Maybe a lot of millionaires, but probably not a lot of billionaires. And I was able to ask all the billionaires in California exactly how many dependents you have, and these are the answers I got. Now I can give you population numbers because we're saying this is the population. So that's why we're using mu instead of X bar. That's why we're using sigma instead of S, because it's a population. So like we did before, the first 2 things we're always going to do is we're going to find the sum of the scores and we're going to find the sum of the squared scores. So on your own, I'd like you to do both of these calculations. So again, get your handy dandy calculator out. Okay. Does anybody have the sum of the numbers? 1, 4, 5, 7, 9, 13, in case you can't see it clearly. Anybody got the first one?
Just to clarify, since there's no repeated values, do we just add them together?
Yep.
Oh, okay.
The thing is, if there are repeated values, you can still add them together, but you can be lazy. You know, if you have the same number repeated several times, you can just keep adding it, or you can say, you know what, I have 5 of those, let me multiply it by 5. There's no repeated numbers, so I just add them. But wouldn't that be the equivalent of saying each one times 1? It's kind of boring, but that's really what we're saying. So what is the first one, anybody?
I got 39.
39, and the second one, anyone? One squared plus 4 squared plus 5 squared, and so on.
Oh, I forgot about the squared. My bad.
341
341. Yeah, this should be fairly simple because there's only 6 numbers, but you got to be careful. And again, I don't take it for granted. I do each one twice because it only took me 15, 20 seconds to do each of these. I said, but I do it twice because my fat fingers can easily hit the wrong button. Sometimes you do things and you get error on your screen, which means you hit maybe a button twice inadvertently or something went wonky. So you always got to do a quick check. Now, I have everything I need to answer every possible question. So let's start with mu. Mu is equal to what quotient? Anybody? What's the quotient that I want to write down that equals mu? Mu is what over what? What numbers?
The sum over.
So what numbers? So it's very specific.
Oh, okay. I need to look back.
Which one goes on top? We should all have the same thing here.
$341.
For the mean.
Oh, okay.
The mean, which one is it? Come on, everybody. It's okay to be wrong, but don't sit back and
It's
say, "Oh, I'm gonna
the
let somebody else
sum,
answer."
the sum divided by the amount of numerators.
Well, you're telling me the formula. I want to know what. Tell me the numbers.
All right, so it would be 39 divided by 6.
Yes, finally somebody bold enough. Yeah, just the sum. It's the sum divided by the number of people. Well, but what are those numbers in this problem? It's that. So what does this turn out to be? This is exactly what?
6.5.
6.5. So my 6 billionaires in California, the mean or the average number of dependents they have in their household is 6.5. Great. So now let's do sigma squared. I do sigma squared before I do sigma because I have to figure out what it is I'm taking the square root of. Now sigma squared, sum of the squared scores, minus the number of people, 6, times the square of the mean. Now, what's my denominator?
Just 6.
It's the whole 6.
It's
It's not 6 minus 1 because this is the population. You remember? In the population, I get the whole group. If it were a sample, what would I be using if this were a sample? What number would I be putting there if this was a sample?
5.
5.
I'd be using 5. So let's calculate this value. Oh, and by the way, if you want to, this is correct. If you're comfortable enough entering that whole thing in your calculator, that way you're correct. Or an easier way to do it, this is what I like to do. Because when I do this, I have to use lots of parentheses. You're lazy, you don't want to use lots of parentheses. You can go like this. Do my numerator, 341 minus 6 times 6.5 squared equals. Now my calculator says 87.5. All right, now I'm going to take that value, I'm going to go divided by 6 equals. And now my calculator says something big and ugly. I'm not writing that number down. I'm taking the square root of that number. So now what do? I hit the square root button and then I hit equals. So I did the numerator equals, divided by 6 equals, and then I hit the square root button. That way it was a little bit safer. I'm less likely to hit a wrong button. So I calculated my numerator completely. Then I calculated my quotient completely. Then I took the square root of what was on my screen. I didn't re-enter the number. You never have to re-enter. Just take the square root of what's on your screen. Now, what number do you see when you did all this? Everyone should be doing this.
3.81.
381.
8.
8. So if we're going to go 2 decimals, what would we say?
3.81.
Are you sure? What's the next number?
Oh, 3.82.
Yeah. Now, why would we do that. Now, a reminder, sometimes we forget. By the way, there is no, in general, if I said how many decimals, the answer is yes. There's no right answer or wrong answer when you say how many decimals. The situation always dictates it. So if you were working for somebody and you're the statistician and you're collecting data, they would tell you, we want this reported to this many decimal places. Because you weren't told anything, 2 decimals is probably enough most of the time. Okay, most of the time, that's plenty of information. You will rarely need to go past 2. I'm just saying that. There's nothing wrong. If you decide to give me 5 decimals, that's fine, but you got to round it correctly. So what did this number look like on my screen? This number looked like 3.81813 on the dot. So if I wanted to go one place, what would I have said? I would have said 3.8. If I'm going to go 2 places, why not 3.81? Well, remember the rule for rounding is you always look at the next number. If the next number is a 0 through 4, then it means you're less than halfway there, you round down. If the next number is a 5 through 9, that means you're more than halfway there, so you round up. That's it. My next number was an 8, so I'd round up. What if I wanted to go 3 decimal places? Would I report 818? What do you think? If I wanted to go 3 decimals, what would I do? 818? That fourth number's an 8. So would it be 818 or would it be 819?
9.
9. Okay, one more time. I want to go 4 decimals. 8188. The next number's a 1. So would I go 8188 or 8189?
8188.
88, because the next number is only a 1. That's it. Now, here, the funny thing is, I can take a group of calculus folks who are really, really great at math. I can give them all the same number and then say, now round it off. And most of them will give me the wrong answer. They have a calculator. They're really smart people. But even in calculus, they never learned correctly how to round. And I always thought that was kind of interesting because I always thought that was something you learned as little kids. It's like, how do you round something? So the rule of rounding, you only round things that don't stop. I have a number that goes forever and I need to report a finite number of decimals. We agreed 2 decimals makes sense. But how do I know where to stop? Well, when I go 2 decimal places, I look and say, is the next number more than halfway or less than halfway? If you were at the gas pump, it's the exact same thing. What amount are you paying? Well, is the next decimal 0 through 4 in the pennies, or is it 5 through 9? If it's 5 through 9, you're rounding up 1 penny. If it's 0 through 4, you're rounding down to the nearest penny. It's actually that simple, and it always works that way. So that 3.82, that's kind of now sort of the average distance everybody is from the mean. Okay, so 13 and 1 are the most extreme scores, and the other ones are kind of in the middle. The larger this number is, again, tells me more about the spread. It's not a good or a bad thing, it's just a numerical measurement. So variance is kind of like saying the average squared distance that everything is from the mean. The standard deviation being the square root of that is kind of like saying the average distance everything is from the mean. If the standard deviation and variance are big, they're either both big or they're both small relatively. If they're big, it means I have a really spread out group. There's nothing wrong with saying a group of individuals is spread out. But again, if we're talking about products that I'm manufacturing, that's bad. Now I'm going to give you a simple example because we actually studied this even in calculus. We studied spread and variance and things. So let's imagine for a moment that well, let's say potato chips. Okay, I don't have a lot of vices in my life. I really love a good salty potato chip, some potato chips. So you go to the store and you buy that bag of potato chips and it says, 14.6 ounces. And we all know what happens. You open up the bag and you look inside and hello, 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 hello. There's a long echo because there's a lot of air and maybe the chips are at the bottom. Okay, you guys know what I'm talking about here. And you're looking at the bag, it says 14.6 ounces, but it just looks almost empty. And it might say on the bag, some settling may occur. There's hardly anything there. So you have your own little chip scale at home and you weigh those chips and maybe they come out exactly what it says. But here's the thing. What if you went on the shelf and you open up a bunch of bag of chips and none of them were what they said? They said 14.6 ounces and none of them were. All of them were either way above or all of them were way low. Is this good or bad? This is really bad. If they're all above, that means I'm giving away things for free. I'm giving away product. I said 14.6 ounces, but I put way too much in every bag. I'm losing money when I do that. Oh, okay, well, but what about all the bags that are short? Aren't I getting it back? No, that's actually worse. If I buy something and I am shorted of what it says, it is an absolute federal law enforced by the Department of Weights and Measures that says that item must be replaced or you must be refunded. And if the manufacturer refuses, they look at fines that are overwhelmingly devastating, like millions and millions and millions of dollars kind of fines. You buy that bag of chips that says 14.6 ounces, you get home, it was only 13 ounces. That store has no choice but to replace that item or give you your money back. That is a non-negotiable thing, because if they don't, then you report them and then the store loses all sorts of money. When you short people, by law, you have to replace. If you're too high, you're giving it away. It's a lose-lose. That's why in real life, we want the variance of a product to be very, very small. Now, here's the thing most of you are probably familiar with, okay? I spend a lot of time at Sprouts. Okay, that's a grocery store. I buy a lot of fresh fruits and vegetables, and we eat very healthy. Now, if you're going to buy that 5-pound bag of potatoes, I'll use something simple like that, the 5-pound bag of potatoes. Is there going to be a 5-pound bag of potatoes that ever actually weighs exactly 5 pounds? Now think about that. Will you ever have a 5-pound bag of potatoes that weighs exactly 5 pounds? Anybody? Yes, no?
No.
Why? Why will you never find a 5-pound bag of potatoes that weighs exactly 5 pounds?
Because then they'd have to measure it exactly and it'd be too time consuming.
Well, not only that, is potatoes are all different sizes, aren't they? Oh, so unless I'm going to have, okay, we're almost there. Let me slice this one into 2/3 of a potato. Now we hit the 5 pounds. Everybody understands. To get exactly 5 pounds, I'd have to have a partial potato in some of the bags. So that means every bag is going to be a little bit over or a little bit under. But there's no way you can grab a bunch of potatoes and make it exactly 5. That's actually not physically possible. So if you're like me, you grab 3 or 4 bags and you weigh them and you buy the 5-pound bag that's like 5 1/4 pounds. You don't buy the 5-pound bag that's 4.5 pounds. Everybody understand what I'm talking about? I have fun with this, but if they say 5-pound bags, half of them are going to be more than 5 pounds, because you can't make potatoes all fit exactly the same mold. So I always weigh a few of them and I grab the one that's heavier. I'm getting extra potatoes. There's no way around it. Now, if you're unwise, you're grabbing the one that's short, but it's short because another potato would have put them way over. So they're going to be a little bit short. That's always going to be there. So when it comes to variance, 5-pound bags of potatoes, they're going to vary a lot, again, because potatoes are different sizes. When it comes to variance, we like to limit the size of the spread if it's products, if it's waiting times at a restaurant, if it's, I have all these bottles that I'm filling and they're all over the place. No, I'd like consistency, because inconsistency can cost me money. Okay, if you're talking about an athlete and you have an athlete that performs at the same level and then another athlete who's all over the map, we used basketball points per game as an example. The one who's steady and consistent is the one you'd say you can probably count on that athlete. Okay, some of you are probably watching the Winter Olympics, and I'm finding it very interesting. All the wipeouts I find very interesting, all the different skiing events. But they'll have an athlete, they do something 3 times, and maybe 2 of their runs were fantastic, and one of them they wiped out. And then there'll be another athlete that had 3 times, and they have almost the same score all 3 times. Maybe they didn't win, but they had the same score. All those crazy snowboarding things where they're flipping around or skiing down the hill backwards. Some of you have seen these, but you'll see some of them will have essentially the same score 3 times. You're going, now that athlete is very, very consistent, but they may not win. The one that wins might be all over the map, but they had that one great score. So it's kind of an interesting effect when you're watching it in the Olympics case. Now, how do I use standard deviation? Well, I'm going to ask you a question. I'm going to give you two different scenarios. Okay. I'm going to give you two different pictures. Hopefully you can see this clearly. Here's a class where the mean of the class was 75. There's a lot of people. It's a huge class. The mean was 75, but the scores are fairly tightly together. I don't know if you got to see this. Oh no, oh boy. Let me put it right there. Okay, I see the glare. 75 is the mean, and here's a score of 80. And you notice in my picture, 80 looks like one of the highest scores. Can everybody see that? In my picture, 80 would be one of the highest scores because of how they're spread out. Now here's another class. They had the same mean of 75, and here's a score of 80. So in the first case, 80 looks like one of the highest scores because the scores are so tightly clustered. This is at the far right end. But over here, these scores are so spread out that 80 is practically in the middle. Now, think about this logically. I have two different classes that had the same mean, 75, and you grabbed an individual in each class that scored the same score, 80. But would you say this 80 is way better than this 80? Anybody want to say that? This 80 is at the top of the class. This 80 is still close to the middle of the class. That sounds really, really crazy. It has to do with spread. So when we're talking about values relative to other values, I have a whole group of values, whether it's a sample or a population. I have a lot of values. I want to look at one value. Now, I can calculate the mean, I can calculate the variance and standard deviation. From that information, I can tell you, is that value close to the middle? Is it high? Is it low? Is it really good? Is it not good? So the example I used earlier, I said, somebody tells me, oh, I got 80 on a test. And I'll say, okay, is that good or bad? Oh, the class average was 75. Okay, so you scored above average. Oh, but my 80 was the high score in class. Oh my God, that's incredible. Right? Each time you told me something, I have a different conclusion. But someone else might say, well, our standard deviation was huge, so my 80 was barely above average. Someone else might say my 80 was the high score. What's the difference? The most important value is not the score. The most important value, believe it or not, is how many standard deviations above or below the mean was that score. What? Yeah. So let me give you a really simple. I want this to make sense because I'm introducing something you may never have heard of, but this is used in every aspect of real life. Okay. It's called a z-score. A z-score is the most important measurement that you can have when you're trying to determine if something's good or bad, if it's high or low, is it exceptional? You've probably all heard the term, classes that grade on a curve. You've probably never had one that actually did, but the concept of grading on a curve means you're not using the person's actual score, you're using their z-score. You're using how far above or below average are they. So the z-score, and by the way, when we do z-scores, it's almost always going to be a sample. It's probably almost never going to be a population. So I really want to concentrate on the sample. The z-score, but I'm going to write for both population and it's the same formula.
Are they solved differently depending on which one it is?
No, but it's, do I have mu or do I have X bar? Do I have sigma or do I have S? It's the same formula. In words, it's exactly the same formula. But like I said before, you are rarely going to have population information, but occasionally you do. If it's a population, it's the individual score minus the mean. That's how far above or below average you are, because that could be positive or negative, divided by the standard deviation. If it's a sample, it's your score minus the mean divided by the standard deviation. It's the same formula, but is it population or is it sample? And like I said, it's probably going to be this because most of the time. So here's what it means in simple English, okay? If the standard deviation is large, then your z-score is probably not going to be very big. If your standard deviation is small, then your z-score is probably going to be much bigger because the scores are tightly spread. So I'll give you an example. All right, on a certain test, I'll be really general. On a certain test, okay, there was a test and the class average, let's say, was 75 and the class standard deviation was 10. Okay. You individually, your score was a 90. Okay, your score was a 90. What is your z-score? Your z-score would be 90 minus the mean divided by the standard deviation. That's it. And that in this case would be exactly 1.5. Now, for whatever reason, because we often look these up in tables and stuff, it is common to report z-score to 2 decimals. You can report it to as many as you want, but 2 is kind of the universal norm that we'll see. As you got a z-score of 1.5. That means you're exactly 1.5 standard deviations above the mean. If the standard deviation is 10, then 85 would be 1 standard deviation above the mean, and 65 would be 1 standard deviation below the mean. Oh, okay. 95 would be 2 standard deviations above, 55 would be 2 standard deviations below, and so on. The z-score tells me the most information. Now, just so you know, and we're going to show this much later in the course, but in most situations, about 68% of the scores are within one, I'm going to call it SD, 1 standard deviation of the mean in most situations. So that means roughly 2/3 of all outcomes are generally within 1 standard deviation of the mean. What's even crazier is, let me write it. About 95% are within 2 standard deviations of the mean. So if somebody had a test score that was 2 standard deviations above the mean, that's fantastic. They might be the high score in the class. 3 standard deviations above or below the mean is really hard to get. I mean, you're extreme at that point, and rarely do you ever see anything beyond 3, strangely enough. So when I have my group of scores, the outer reaches are usually within 3 or maybe even within 2. So if someone told me they got a z-score of 1.5, that's really, really good. That is really, really good. Okay. Now, do you know what uses z-scores? SATs, MCATs, GREs, standardized tests in general, you're using z-scores, but you didn't realize it. In an SAT, okay, in an SAT, we always say, well, what is the average in an SAT? Let's just say you did the SAT for English. The mean is 500. Does anybody know what the high and the low on an SAT is? What's the highest score you can get on that SAT?
Is it 1,500?
Well, no, on the one test, just English. It's the same for math. 500 is in the middle. The low would be 200, and the high is 800. Every now and then you'll hear about someone, they got 800 on their English, or they got 800 on their math. You guys ever hear things like that?
I do.
Rarely.
Now, what does that mean?
Really?
Here's the crazy thing about an SAT. On an SAT, by the way, this is absolute. This has not changed, but most people aren't aware of how the calculations are made. I'm going to use an SAT. On an SAT, and this is most standardized tests, the mean, and we actually do use it as a population, is 500, and the standard deviation is exactly 100. It's what is called a standardized test. It's scaled, so this would be true. So a score of 500 means you were exactly average. A score of 600 means you were exactly one standard deviation above the mean. A score of 400 would mean you're exactly one standard deviation below the mean. So what would a score of 800 mean?
In the middle. Oh, wait, I'm
800.
sorry. I'm sorry. That would mean it's a lot, like, you know, the best it could be.
That would be 3 standard deviations above. And remember what I said? It is extremely difficult to be 3 standard deviations away. That means that you are extreme. Does it mean you got a perfect score? Not necessarily, but it means you are so far from everybody else. Now, millions of people take the SATs every year, so there's a lot of values. It's really hard to be that far above. A 200, that would mean you're 3 standard deviations below the mean. That means you're extremely at the other end. Does that mean you missed every question? Not necessarily. It means that you're that far away. So an SAT is a great example of a Z-score. The score of 800 would be a Z-score of exactly 3. A score of 700 would be a Z-score of exactly 2, and so on. A score below 500 would present a negative Z-score. Yeah, Lila?
Since we're on the topic of z-scores, standard deviation, and curving, I heard that a lot of the UC schools use like curving often, and they often curve down, and I don't understand why.
It's not, there are places in culture, in life, there are places that actually do use curves. In an academic situation, I've never actually heard of one, except medical school is about the only place I've ever heard. What usually happens is an instructor gives an exam, the scores aren't very good, and so they say, I'm going to curve the exams. No, they're not. They're going to do what's called scaling. They're going to artificially add a number of points to everybody's score. Just they're going to make it so that scores don't look bad. A curve means first of all, you're ranked, and you're graded based on how everyone else did, which means if you score near the average, the highest you can get is a C. Now, here's why curving, I think, is a terrible thing in general. I teach Calculus 3 and things like that. I have a Calculus 3 class. Almost every semester, my Calculus 3 class usually has a class average around 90%. If I graded on a curve, the 90% is a C. But 100% would only be a B because it's not far enough above the middle. Does that make sense? There's no logic to that. If your average of your class is 90% and you grade on a curve, then 90% is a C. Yikes. that wouldn't be very good. If you have a class of exceptional people, you don't punish them because they're all exceptional. No, you do it that way. Now, flip side, what if you have a class and nobody's passing? You don't say, well, then I'm going to make the C be, 10%, and then that way I can give all these good grades. What about next semester when they, Now, there are situations. There are a lot of situations. You're going to apply for a job. I'll use a simple example because I know people that did this. You're going to apply for a job, let's say, with the fire department. Okay. And there are a lot of applicants. So usually they'll give some form of a test, a written test, because they want to weed out the applicants and take maybe the best ones. Okay. So maybe 1,000 people applied, but they want to weed it down to maybe 100. And then they can go further with those. Or maybe they want to weed it down to 10. I don't know. But I know people who went through this. So they maybe take a series of tests. But the thing is that how do they know which ones to do? Well, they said, I'm only going to take the top 10% or the top whatever. That means they take every single score and they rank them and they put them on a plot. And then they say, we're only going to take the people whose Z-score is above a certain number. Because then the computer can spit out all the names. That would be an example of grading on a curve, if you will, because I'm trying to reach certain applicants. This is not terribly common. And in an academic situation, it's really unusual. And I hear things all the time. People say they're graded on a curve. Probably not, because it's unlikely the instructor actually knows the mathematics. The curve is 100% statistics. And a little bit later, when we actually get to the mathematics of describing that, it'll be really obvious to you guys. Go, oh, that's all it means. Okay. First of all, you have to have that bell-shaped curve, and then you're talking everything's based on standard deviations and things like that. In simple English, if you're grading on a curve, that means you say everybody who has a Z-score higher than this gets an A. If you're in this range, you get a B. If you're in this range, you get a C, and so on. That's what grading on a curve would be. But that's really unusual to do that. in an environment like a UC where the students in general are already going to be really good, you don't decide that all of a sudden what used to be an A is now going to be a C. That's kind of a tricky one. Anyway, we don't do that here, but we want to understand. So in an SAT, for example, your Z-score is easy to calculate because of the fact that the numbers are made much, much friendlier. So
I had a quick question,
Oh,
sorry.
yeah, go ahead.
So for the example you just gave with the SAT, the denominator or the sigma is 100 because that's the population, or what was the
No,
explanation behind that?
yeah. If it's an SAT,
Okay.
we really consider it a population because in an SAT,
Okay,
let's say, I don't know the exact numbers. I know it's per year, there are millions of people taking an SAT. So what we do is we say, let's take all of the people this year who took the SAT. That's not a sample, that's the population. Now, when we do all the calculations, we come up with what's the mean and the standard deviation, and then we call it standardize it. We make it so that's the standard deviation and that's the mean.
all right.
It's a
Yeah,
little bit funky.
I'm just writing it down, the example, and actually pointing arrows to why that number is going in the denominator spot. And I just wanted a quick explanation.
Yeah, imagine it this way. Let's say there's 100 questions and the average number of right answers was 50. Let's just make it really easy. Then what we're going to do is we're going to say, okay, let me take that average and multiply it by 10 so that it's 500. I want to make 500 my average because it's a more convenient number. What if my standard deviation was 25? Then I'm going to multiply it by 4 to make it 100. We're going to scale it so that it is really convenient. So every single year when I give those scores, they're always the same range of scores. This is called standardizing. Anytime you take a standardized test, most of you have probably taken them even when you were kids. Every year, if you think about it, you'll go back to 4th grade, 5th grade, 6th grade, you probably took a test in the spring that measured everything you had learned up till then. And it wasn't the test for your classroom, it was some test from the state of California. Does anybody know what I'm talking about? The Stanford aptitude tests, for example, that was a really common one given for many, many years. There are different versions. And these tests are designed to measure, where you are in your education, but they're standardized. The GRE, that's the graduate school. That's sort of like the graduate version of the SAT. There's the MCAT, that's the one to get into med school. There's the LSAT, that's the one to get into law school. There's the GMAT, that's the one to get into business school. There are so many versions of standardized tests, but they all have the same sort of basic formula, and they're based on Z-scores because the school you're applying to may say, we're only going to take scores above this. They'll do that, make it easier on them to keep track of. But here's my big question now today. This is where you got to do a little thinking. You have a friend, and they're taking, let's make it simple. Let's say you're both taking stats. And you both have your first exam coming up. Now, they could be a student in my class. They could be a student in somebody else's class, but they're also taking stats. Okay. And you both just took a test and you'd like to know who did better. Well, the first thing you could say is, well, who had a higher score? But what if your test was out of 200 and their test was out of 400? They're probably going to have a higher score, aren't they? So that may not be the most effective way. You could say who had a higher percentage. What if they had a higher percentage, but their test was really, really simple and everybody in the class had a high percentage? Do you see what I'm getting at? How do you compare the two? You compare your Z-scores. So here's the things. Student 1, student 2. Okay, student 1 had a score, let's say their score was 150 and their class average was 121.6. Their class standard deviation was 18.34. We had all the numbers. We did these calculations. That's what they were. So I'm just going to hand you that information. Okay. So student 1 scores 150 where their class had this average and this standard deviation. Student number 2 scored 375. And I'm going to call it, let's call it S1, student 1. So the second set, but their class had a mean of 343.8, and they had a standard deviation of let's say 31.62. Okay, these are reasonable. Now, obviously, this test. Can you? Oh, sorry, you guys can't see. Let me put that down. Sorry, I'm looking at the glare. 150. Sorry about that. Obviously, this test was worth a lot more than this test. Don't you agree? How do you know? Because they both scored above average. They both scored way above average. Great. So who did better? On the surface, really quickly, who did better? Well, you say, well, this person got 375. But their test might have been out of 500. This person got 150. Maybe their test was out of 200. So it's hard to say who did better just because they scored more. So I use these numbers over here. Here's how we're going to make our conclusion. If you want to know who did better relative to their class, we calculate their z-scores. It's actually that simple. And so who wins? Who had the higher z-score? The z-score tells me how I did relative to the other people in the class. Did I score way above them? Did I score barely above them? Did I score way below, barely above? Did I score right at the average? Now, does that necessarily mean they are a better student? No, we just said who did better relative to their class. So let's do person number one's z-score. We'll call it z1. So how do I calculate z1? I take their score, I subtract the mean, and I divide it by the standard deviation. That's simple. Okay, so let's all do that. I said the rule of thumb usually on a z-score is 2 decimals. Okay, on a z-score, 2 decimals is kind of the norm. So tell me when you got a number.
$1.55.
About 1.55, good. Which
Well,
by the way,
already rounded up.
because it's 1548, so we round it
yeah.
to 155. Okay. As I said, 2 decimal places is kind of the universal norm. Let me erase this. I don't need this anymore.
Professor,
Yes.
sorry to interrupt you. How are you putting that into the calculator? Because I feel I know for a fact I'm doing it wrong because I'm getting completely different.
Here's what's happening. There's 2 ways to do this. I can calculate my numerator and hit equals and then divide it by 18. Or I put parentheses around my numerator and I divide by 18. I'm going to show you. I'm glad you brought that up because this is a problem that algebra students have all the time. If I want to do a plus b all over c, and I enter into my calculator a plus b divided by c, will that work? No. Order of operations says I just did this. Do you understand? Oh, I have to do this then. So when you have a bunch of stuff going on in the numerator, you surround it with parentheses. Or just simply calculate the numerator and hit equals, then divide it by it. Does that make sense? So you either use parentheses when you enter it, or you just calculate the numerator. It's always okay to do that. Do 150 minus 121.6 equals, then divided by 18.34. And then you'll get that. So everybody make sure if you're not getting 1.55, then try what I suggested, because that's what you should be getting. And like Robert pointed out, I said, I know what the numbers are, but I'm not getting that answer. Is because the lack of parentheses means you were actually doing something slightly different, and that won't work. Okay, so let's make sure everybody's got that one. Now, how about student number 2? They scored 375, and I'm going to subtract their mean, which was 343.8, and I'm going to divide it by their standard deviation. Now let's all do that calculation. So when I'm doing this, I'm lazy. I just do the numerator, 343, okay? I do my numerator, 31.2, and then I divide that by 31.62. That way I know I got it right. Okay, has anybody got a number there?
0.99.
So that's approximately 0.99. Huh. Well, that makes this conclusion fairly simple, doesn't it? Relative to their class, who did better on this test? Student 1 or student 2?
Student 1.
Student one, their Z-score put them way up higher, way up higher. See, it would be really difficult. Now, I'm a huge sports fan. You'd never know that, right? The
And
original.
so, I'm sorry to bother
Yes.
again, but what you said about 68% being one-time standard deviations from the mean, is that
Roughly
standard
68%.
across like most all things, or is it
Not all
particular
things,
to
no.
one thing?
I said most of the time.
Okay,
We'll discuss when it is and when it isn't a
but
little bit later.
for our sake, it's applicable in this class, right?
It's
Okay.
reasonable. Now, for example, there are things that we know a lot about. The human heights, for example, we know basically look like a bell-shaped curve. Duration of pregnancies in women basically look like a bell-shaped curve. Then those numbers become exactly 68% are within one. Exactly 95% are within two, things like that. If we're talking about income or housing, remember we talked about being very skewed? It doesn't apply to those because you're Bill Gateses of the world. Bill Gates is like 50 standard deviations above the mean. I'm not joking. He's so far in terms, because remember, there's no highest income. So if I take the richest person in the country, they're going to be a ridiculous number of standard deviations above the mean. Does that make sense? So it wouldn't apply to that because it's open-ended. But if we're applying it, like I said, human heights, duration of pregnancies, there's a lot of things like that that we actually know enough about to say, yep, those numbers are pretty solid because I'm expecting things to be spread fairly evenly. That's really the key. So going back to this example, this is a fairly easy thing. Now, I said I'm a big sports fan, and anybody who's a sports fan, let's say you're having a discussion with your dad about, back in his day, because my dad does this all the time, back in my day, right? And he'll talk about athletes from his time period. And you guys you've all made these conversations. Well, shoot, if Michael Jordan were playing today, would he be as good relative to his peers? That's a classic question. If Muhammad Ali was still boxing today, I don't mean he's like 90 years old. I mean, a 30-year-old Muhammad Ali was boxing today, would he still dominate relative to his peers? Everybody who's a sports fan over a period of time has had these types of questions. Somebody from a previous era, if you put them today with today's athletes, or vice versa, take somebody who's dominant today and put them back in the day, would they still be as good? That is a very difficult question to answer because there is no absolute right answer. So if you talk about how good somebody was, what you often do is say, how good were they relative to their peers? And then take the athlete today, how good are they relative to their peers today? That's probably a safer way to compare them because you can't go back in time or take somebody from the past and bring them today. That just doesn't work. And so most people automatically say, well, today's athletes and today's performers are so much better than the old days. I don't think so. I watched Michael Jordan play. And I still think he would dominate today. I saw Muhammad Ali box. I think he would still dominate today. I saw athletes from previous generations. If they were playing today, I think they'd still do fine. So that question of how do you compare people from different eras, it's a difficult question. There's no right answer, but this is a starting point. So I want to compare results from different classes even. Then comparing Z-scores is probably the safest way of doing it. Okay, now I'm going to stop there. Hold on.